Welcome students. While we are studying the last class, that is in the last video, while we are studying about the electrical flux in case of an uniform electrical field, I have got the expression as flux available phi of E is equal to E vector dot A vector, and the magnitude is given by E into A into cos theta. That I have represented two special cases. What is the first special case? If I am saying that theta is equal to 0 degree, then we can say the flux available phi E is maximum, that is product of electrical field and area. See, if theta is equal to 0, then we can say the plane is the area that we have considered, plane of the area is perpendicular to the electrical field E. Are you clear about this? That was the doubt I have raised in my previous video, whether you can able to understand this concept. See, here I am putting theta is equal to 0 and I am saying the plane of the area is perpendicular. So you have to look at the definition for theta. What is theta? Theta means, theta is the angle between the normal drawn to the area, normal to area, and electrical field, and the direction of electrical field. See, can you able to understand this? And diagrammatically I will be representing. You see, you are representing the electrical field by drawing parallel lines. Okay. In this, if you are considering the area, plane of the area perpendicular to the electrical field, uniform electrical field, then we are saying theta equal to 0. But plane is perpendicular. See, plane of the area is perpendicular to E. What is this theta 0? You have to, first of all, then you have to draw the normal to this area. So I am drawing it with the help of what? I am drawing it with the help of one red color line. So normal to the area, I am marking it as n cap. Now you find the angle theta. Angle between this red line and angle between this yellow line will become 0. That is considered to be the angle between normal to the area and the electrical field. If that is the case, then we can say the plane of this area A is perpendicular to the electrical field. Similarly, what is the second part that I have explained? What is the second part that I have explained is, if theta is equal to 90 degree, if theta is equal to 90 degree, then we can say the flux available in that electrical flux available is equal to 0. That is, here I can say the plane of the area, we have considered an area, isn't it? For that area, when you are considering the plane of the area is parallel to the electrical field E vector. So if the electrical lines and the plane of the area are parallel, then angle theta is equal to 90. That is angle between the normal drawn, angle between the normal and the electrical lines available E vector is considered to be perpendicular to each other. That is what I am putting it as theta as 90. If you want to represent it with the help of a diagram, let us represent it. If you can consider these lines as parallel lines which are taken to be mentioning an uniform electrical field, and if I am considering an area parallel to that of what? Parallel to that of the electrical field, then the normal drawn n vector and the direction of the electrical field both are considered to be perpendicular to each other. So I am putting it as theta is equal to 90. That was when you are putting theta is equal to 90, plane is parallel, when you are considering theta equal to 0, the plane is perpendicular. I think you are clear with this idea. Now, what is the thing we have to study in the next concept? the next concept that we are going to study is electrical flux. Okay, we are going to study is electrical flux in a non-uniform electric field, and also in a non-uniform electrical field, and the area considered is an arbitrary area, and in an arbitrary area. See, what do you mean by this? In our previous case, we have considered a uniform electrical field, and the area that I have taken is an regularly shaped area, and for that we have calculated the flux as phi E is equal to, what is that value? We have written it as E vector dot A vector, which is equal to E into A into cos theta. Now I am going to calculate the same electrical flux phi E. But instead of considering a uniform electrical field, I am going to consider a non-uniform electrical field. And the area is not an regularly formed area or not an regularly shaped area, any form of area. So we are giving it out as an arbitrary area. So how I can able to consider this concept? First of all, in order to explain this, I am taking a non-uniform electrical field. See, the uniform electrical field means it is represented by parallel lines. Non-uniform electrical field means it is not having parallel lines. It may be of any shape. That is, electrical field is considered to be not same at all points. See, it may be like this or it may be like this. So the electrical field available is not considered to be what? The electrical field available is not considered to be parallel to each other. So if the electrical field available is not parallel to each other means it is a non-uniform electrical field. If I am considering this non-uniform electrical field, the electrical field at each and every point may be different. Here it may be E1. If I am taking here, it may be E2. If I am taking here, it may be E3. And here, if I am taking here, it may be E4. Like that, the electrical field is considered to be different at different places. It is not considered to be same. Similarly, I am considering an arbitrary area kept inside this electrical field. So an arbitrary area means any area which was considered to be not flat first of all, and that area may be of any shape, and the area is not considered to be of an regular shape. So in this case, how you can able to calculate the electrical flux? So in order to calculate the electrical flux in this case, what I am doing is I am separating the entire area into small area segments. What do you mean by that? See, the whole area that is available here is separated into small areas, infinitesimally small areas. If I am considering small areas like this, see each and every area, this area I am taking it as delta A1 available in the electrical field E1, and I am considering this small area as delta A2 available in the electrical field E2. Similarly, I am considering this as delta A3 available in E3. Similarly, delta A4 available in E4, etc. So what I have done? Is the flat area or the entire area, okay, the entire area is divided into infinitesimally small. So if I am considering the areas as small areas, each small area, okay, each small area is almost flat, is almost what? Is almost flat. And when you are considering the electrical field E vector, the electrical field E vector is almost constant or we can say same. See, the electrical field E vector through each area is considered to be uniform. See, when you are considering the total area, then the total area is not available in an uniform electrical field. It is said to be in a non-uniform electrical field. The electrical field at different points are considered to be different. So we are saying it as non-uniform electrical field. So in order to calculate the flux for that area, what I have considered is the entire area or the whole area is divided into small areas. See, each and every small area is now almost flat. And in that small area, when you are considering the electrical field is taken to be more or less uniform. So we have to consider it as what? We have to consider it as uniform. So we have to take any one of the, now you consider any one of the area. If you are taking any one of the area, if I am taking this delta A1, which is available in this electrical field E1, for this area, you drop a normal. When you are dropping a normal for this area, if you are dropping a normal to this, let us consider it as n cap, or I can consider it as, see, since this is delta A1, I am writing like this, delta A1 vector. That is delta A1, the magnitude of the area multiplied with n cap, then I can say it out as what? Then I can say it out as delta A1. Now, for this small area, what is the electrical flux? For this small area, the electrical flux I can written as phi E1. So, that is the electrical flux for this area due to E1 is equal to E into, or I can write E1 vector into delta A1 vector, or I can write the dot product as modulus of E1 vector as E1 and the modulus of area, that is delta A1 into cos theta. Similarly, I can write it for delta A2, then I can write it for delta A3, delta A4, etc. There I can get, see, in the first case I can get pi E1. Similarly, I can get the flux for the second area, then the flux for the third area. Like this I can move on. So, what I am going to do? In order to calculate the total flux, since the entire area is divided into small areas and each and every small area is almost flat and the electrical field is taken to be uniform, then I can consider the total electrical flux. Then I can write the total electric flux through the entire area is, through the entire or the whole area, through the entire area, capital A, is approximately equal to, because we have made an approximation as the small areas inside which the electrical field is considered to be uniform, approximately equal to phi of E, the total electrical flux. What is this total electrical flux phi of E, which is equal to vector sum, that is the flux available E1 vector dot delta A1 vector, that is the flux for the first area, plus I can write E2 vector dot delta A2 vector, plus then E3 vector dot delta A3 vector, plus etc. up to what? Up to the nth area. So if you are considering nth area, then the electrical field available is En multiplied with delta An vector. So this is delta, not A, this is delta. So this we are calling it out as what? This we are considering or taking it out as the total flux that is available for that entire area available. Okay. See, now when you are writing this in terms of a mathematical form, so if you want to write it out in a mathematical form, let us consider in general. See, in general, that is I am going to apply a limit. What is that? In general, if that area considered delta A, all the areas that I am considering delta AI is tending towards 0. That is tending towards 0 means the value of that area is considered to be very, very, very small. That is for all elements, for all I, okay, for all values of, that is 1, 2, 3, 4, etc. up to I. So for all values of I, if the area considered is taken to be very, very small, that is I am going to apply a limit. What is that limit? The limit is if delta of AI tends to 0, then how I can write the flux? Then the total flux, then I can write the total flux as how? Then the total flux can be written as, then the total flux for the entire area. So the total flux for the entire area can be written as phi of E is equal to, so I can write it out in terms of what? In terms of summation. First of all, they see here itself I can write it out in terms of summation. See, first of all, before this value itself can be written in terms of what? This value itself can be written in summation. That is phi E is equal to, how I can write this value? Phi E can be written as, see, I can write this. Phi E is equal to sigma of, here I am writing it as E of I dot delta of what? Delta of AI vector, where I ranges from 1 to n. So this equation phi E can be written mathematically as what? Written mathematically as phi E is equal to sigma of I is equal to 1 to n EI vector dot delta AI vector. Now you apply this. After this you apply the approximation. What is the approximation? In general, in case of limit, what is that limit that I am applying? If delta AI tends to 0 for all I, then the total flux that I am getting is available. The total flux that I am writing can be written as, total flux available is delta phi E is equal to integral of, instead of sigma, because delta I is taken to be very small, integral of E vector dot dA vector. So integral of EA vector dot dA vector, that can be written as integral of, what is this value or what is this magnitude? Modulus of E vector is E, modulus of dA vector is dA into cosine of the angle, that is cos theta. See, from this relation, okay, I can say from this it is clear that, okay, I can say that from this it is clear that that is I am going to say the flux depends on, it is clear that the electric flux depends upon, okay, what are the factors on which the electrical flux is depending. So from this it is clear that electrical flux, you see the formula, electrical flux for a given surface, depends on both, you can see the electrical field as well as the area. The area is dA vector, so orientation of the surface with the electrical field. So depends on both electrical field. That electrical field I am writing it as E vector, and also it depends upon dA vector. dA vector is orientation of the surface. Orientation is nothing but position. Orientation of the surface with the electrical field. That is dA cos theta with the electrical field. I think you are clear about this idea. So let us summarize what I have dealt with this. See what I have dealt, two concepts I have dealt here. One, already what I have told in our last video, that final part is again explained here. See the final part, That is, when you are considering about the electrical field in an or electrical flux in an uniform electrical field, in that case we are saying that the electrical field is given by the formula phi E is equal to, okay, phi E is equal to E vector dot A vector, that is EA cos theta. Here, if this theta is taken, angle between normal to the area and the electrical field. If theta is 0 means plane of the area is perpendicular to the electrical field. I have explained it with the help of drawing a diagram. The uniform electrical field is represented by parallel lines. The plane is perpendicular to the electrical field. What is angle? If you want to calculate the angle, drop a normal. Now the normal and the electrical field are parallel. So theta is 0. So if the angle theta is 0, plane is perpendicular to electrical field. What is the second concept? If theta is equal to 90, then we can say that the total flux available is equal to 0. That is, plane of the area is parallel to the electrical field. If theta is 90 means, you see, here the plane is parallel to the plane here, the red color line, and the electrical field is yellow color line. If you are dropping a normal, then the angle between the normal and the electrical field is 90, but the plane is parallel. So the flux available is 0. I think you are very clear about the final part that I have dealt in the last video. What is the next concept that we have to see? Already we have studied the electrical flux in an uniform electrical field. If you are considering the electrical flux in an uniform electrical field, then it is given by phi E is equal to E vector dot A vector, that is equal to EA into cos theta. In this case, the electrical field is considered to be uniform, drawn by parallel lines, and the area that I have considered is what? The area that I have considered is a regularly shaped area. It is having a particular shape. Now, what I am going to consider? I am going to consider the same electrical flux. But here, the electrical field is taken to be non-uniform. And the area that I have considered is of any shape. That I am taking it out as an arbitrary shape. So in order to explain this, what I have considered a non-uniform electrical field. Non-uniform electrical field is represented by drawing so many number of lines which are not parallel to each other. What do you mean by this? That is, if you are considering different points inside this electrical field, at the different points you are having different values of electrical field. See, I have taken a line here which is having an electrical field E1. Here I have taken a line or a point where the electrical field is E2. Here I have considered that the line is E3. Like this it is going on. Now, inside this I have considered an area of irregular shape, of any shape. So I have given it out as an arbitrary shape. If it is an arbitrary shape, moreover, the shape was not considered to be flat. I have not taken it out as what? I have not taken it out as a flat area. I have taken it as an any shape. Now, if you want to calculate the electrical field for that arbitrary area, what you are going to do or how you can able to get. So, in order to get the electrical flux for this arbitrary area in non-uniform electrical field, what I am first of all doing is the whole area or the entire area, I am dividing it into small areas. That each and every small area I am representing it as delta A1, delta A2, delta A3, like that. If you are combining all that small areas, you will be able to get the total area. So that I have written it there. Entire area is divided into small areas. See, if you are dividing it into small areas, then each and every small area can be considered as a flat surface, and moreover, the electrical field available inside that small area is considered to be uniform. We have to assume. See, the area is very small means the variation in the electrical field is also considered to be negligible. So, we are taking it as the electrical field is taken to be uniform inside that small area. Now, I have to calculate the electrical flux for each and every small area. For example, I have calculated for only one area. So, I have taken an area delta A1. For that area delta A1, if you are dropping a normal, then it is n cap, or I can represent it as delta A1 vector. Now flux available is flux of E1 is equal to E1 vector dot delta of A1, or I can write E1 delta A1 cos theta. Similarly, I can calculate the electrical flux available for each and every small areas. After calculating for each and every small areas, I can apply it what? I can add all that values to get the total flux. So the total flux through the entire area is approximately given by phi of E, which we are writing it as what? Which we are writing it as phi E is equal to the flux due to the first area E1 vector dot delta A1 vector plus EA2 vector dot delta A2 vector plus EA3 vector. I am considering it as EA3 dot delta A3 vector. Like that it is going on. Now what I can do, you just come here, see, while writing I have forgotten, so I have written it on the side. See here, you have to consider the next line of this is this one. You have to consider here. What I have written? I have written this value in mathematical form in terms of sigma. You see, when you are writing it in terms of sigma, you are able to get it out as phi of E is equal to sigma of EI vector dot delta of AI vector. What is that I? That value of I varies from 1 to n. The value of I varies from what? Varies from 1 to n. So this is considered to be a mathematical notation in terms of sigma, summation. Now I am going to apply an approximation. What is that approximation? See, when you are considering this delta AI, that is for all values of small area, delta A1, delta A2, delta A3, delta A4, etc. up to delta AI, if that area go on decreasing, smaller and smaller, tending to 0, that I have written. If I am applying a limit that delta AI is equal to or tends to 0 for all I, then the total electrical flux for the entire area is given as phi E is equal to, removing the summation, I have put the integral of E vector dot dA vector. If you want, you can write here limit delta of A tends to 0. While you are studying calculus in mathematics, you might have known this. So we can removing this summation and considering this limit delta I tends to 0, I have to write this flux in the electric flux due to the electrical field in that given arbitrary area as integral of E vector dot dA vector, that is equal to integral of E into modulus of E vector modulus of dA vector into cos theta. So from this it is clear that the electrical flux for the given surface depends on both the electrical field E, and here it is dA vector or dA cos theta, what we are saying it as orientation of the surface with the electrical field. You may expect this in a 3-mark question. Hope you should have understood. Thank you.